Thank you for being here. I'm Zdeněk from Codasip. And what I'd like to talk about today is RISC-V customization without re-verifying everything, or how to minimize the verification effort if you do the custom extensions. So first of all, let me try to build the business case why we are looking at this problem in the first place. And then I will go through the solution that we came up with to this problem, followed by a few case studies proving the point. And then we have some future steps or remarks or key things to remember from this presentation. So let me start with the sort of business case or the motivation for this work. And well, if you look at the semiconductor scaling and rules, it's reaching its limits. So you can see that after more than 50 years of driving, some rules either already stopped working or it's slowing down. So things like the Reynolds-Cayley, Camden's law, those are clear. Depending on which camp you are, you can claim whether the Moore's law is still active or slowing down. But nonetheless, we need to look at the ways how we can provide more performance, more power to the upcoming challenges that we are facing, such as AI and so forth. So yeah, we can say that we can go to the smaller nodes, but it's becoming quite expensive these days. Or you can do some fundamental change, like going for optics or kind of carbon nanotubes. But you can then claim that maybe these things are not mature enough to be deployed widely. So what else do we have? Well, we have something that's called heterogeneous compute or custom compute, and we have proof points, in this summit, previous summits, that this is actually a way how we can solve the demand for more powerful devices that we need for whatever purpose. Now, the heterogeneous compute is obviously not new. It has been here for a while, and actually it has different, let's say, forms. Because on the left side, you can see that we can maybe differentiate only on the software by having smart people, smart algorithms, and you can have a better solution. Or you can do some customization on the SoC level, so you can pick and choose the individual IPs that fits you the best. So if you are sorting out some DSP problems, that you're going to choose a different IP than if you are solving the AI problem. But we can go even beyond that, and you can go and you can customize even individual pieces in the SoC. And in this talk, we will focus on the processors, and because these are usually the hearts of the systems where you gain the most. But if you start with IPs and you start customizing it, on the first side, you say, oh, great, I'm going to get all these benefits in terms of the performance or power reduction or whatever. But then on the second thought, you will start realizing that actually, well, if I start touching the things, then we need to re-verify it. And if you look at some surveys, you will find out that the verification is a big portion of it, a big portion of the resources that you need to put in, which means the money in the end of the day. So then a couple of people say, well, maybe I'm not into that because I cannot afford it, or I don't have a team who is skilled enough to do it. So we looked at this problem, we came up with a solution of this problem. Before I dive into the solution itself, let me just make one more remark, and that's that the IP or the RTL is just a part of the problem, because if you do the customization, you need to deal with the SDK as well. So some automation or some, let's say, ways or new ways how to approach this is also needed, because if you do custom instructions, then preferably you have a compiler that is able to use these instructions fully automatically without going to the assembly, unless you want to, of course. So there is this second part of this of the problem of the customization, how to deal with the SDK. But again, this is just a note. I won't dive into the detail because Codasip has a solution for this one, but I won't dive into the detail, and we will stay on the RTL side and the verification side for the rest of the talk. So how we actually can lower down the verification effort and enable the customization to the wider audience. So we've created a new methodology that we called bounded customization. And as the name suggests, is a bounded. So there is some sandbox in which you need to stay to benefit from the fact that you don't have to re-verify the whole core. The thing is that we enhance the IPs that we have, which, by the way, we have all sorts of the RISC-V processors, starting from the embedded to application class CPU. And we've created this purple box in them, this sandbox, in which you can fit the custom instructions. There is a set of rules that you need to follow. And if you follow them, you can benefit from the fact that no matter what you put inside, you can't break the core. We guarantee that you can't break the core. Now, the set of rules are implemented in a certain way, and I have a slide on this one. And the other thing that comes with this approach is that we would like to lower the barrier for the customization, so then even, let's say, the software engineers can do it, and not only the hardware guys. Because whenever I talk to some software engineers, they always say, oh, I wish I had this instruction or that instruction that hardware guys may not know, but the software guys know it. So the other thing with the boundary customization is that we would like to enable these guys to do the customization or design space exploration as well. But coming back to the rules. So we came up with a simple set of the rules. You can see them on this slide. If I go through them quickly, so one of the rules, or the rules are as follows, which means that, okay, the source and destination has to be either already existing register file, either general purpose, FPU, and so on, or it can be your own new registers that lives inside of this sandbox. And in the case of the source operand, obviously the immediates. You can read CSRs if there is a CSR without side effects, but you can't write because write can, again, trigger some side effects that you don't want to have, and suddenly you are out of the bounds. There is only one supported exception that you can throw to make things and life easier. Obviously, you can't change the top-level interface of the CPU because that it breaks the top-level verification. Test benches that ships with the IP. And there has to be certain limit on the cycles that you need to have, so the instructions that take multiple cycles can actually finish to avoid the deadlocks and so on. Now, these rules are obviously captured in the generic form, which is some sort of YAML configuration. And therefore, you can play and tune with them if you want to. And then as for the barriers, as I mentioned, we need to lower it down. And this is done through the high-level description language that we use to capture the custom instructions. So then the custom instructions doesn't require all the deep knowledge about the microarchitecture or the CPU that you are putting instructions in, because this is what the tools do for you, or tools does for you. Which means that all this hazard handling and the pipeline control stuff, this is done by the tooling automatically, and you focus as a designer only on the instructions and the semantics of them. So let's look at how we implemented these rules and these, let's say, the barrier lowering inside of our solutions. So we have a tool that's called Codasip Fusion. As I mentioned, it takes the processor description in the high-level description language called Codal. You describe the whole CPU or part of the CPU in it. Then you throw it to the studio, and studio then generates a couple of different things. It generates obviously the RTL, but it doesn't stop there. It generates also the verification test benches, the SDK that I mentioned at the beginning. So you have the compiler and profilers, simulators, and so on. But what we had to do on top of that is that we need to implement the enforcing of the rules. So the EDA tool actually enforces the rules, and if you break them, you got a nice message that either you do it intentionally or unintentionally. You have the message saying you are out of the bounds, which might be okay, but then you need to pay the penalty of the verification. But if you would like to stay within the bounds, the tool tells you so, and it kind of narrows the path for you, and then you can see where you are. Besides the tooling itself, as I mentioned, we provide the IPs, pretty much every single IP that we have, which varies from the embedded to the application class CPU. They have this bounding customization block over here. And this is just an example of one of them. And these bounding customization blocks are designed in a way that if you design custom instructions, say for the embedded class, you can really easily move them to the application class without changing a single line of it, unless you want to, because you don't need to have different timing, for instance. But you can really easily move and swap the extensions like a plug and play thing across the board, because again, we designed the methodology in this way. So from the customer point of view, it looks quite simple, because what you're going to get is one of the IPs, then a studio, and what you need to focus on is only this block, because the rest is taken care by Codasip, so we guarantee that the core is really high quality. It comes or ships with the test benches, either formal or functional, and then all you need to do is just do your stuff, because you need to verify your instructions. We can't do it for you, or we can, but we assume that you would like to do it. So we don't have to see the custom instructions at all. It's all your IP in the end. And then you click on the button in the studio, and studio gives you all you need. So how it looks like in the real life. So you get the studio, as I mentioned, that enforces the rules. And it looks like this, for instance. So if you open the UI, you will see the files that are locked, and you can't touch, because those are locked. And you can see the files that are meant to be changed, and you can easily distinguish between those two. And if you try to break it, you will see an error messages. Even if you try to break it in the console, the studio then during the compilation will shout anyhow that you did something wrong. And then as for the lowering the barrier, all you need to do as a user is to define the mnemonics of instructions. You need to define the type, or the source and destination registers that the instruction takes, and then define the behavior of it. So as you can see, it's quite easy, because all of the rest of the decoder stuff and pipeline propagation, this is handled by the tool for you, and we guarantee that this is okay, it's verified, no problem in there. And all you need to do is just focus on this part, because this is what you need to define in the end of the day. But as you can see, there is no encoding of instructions, because that's inferred automatically. And there are no pipeline information, because that's inferred automatically too. And you can say whether it's, again, single cycle, multi-cycle, and all these sort of things. So it's quite, let's say, I believe, easy to use. And what we get as a feedback from the guys from the software side is that suddenly they can do magic or design space exploration quite efficiently. So let's look at the two case studies. I mean, we did a bunch of them, and the customers did as well, but I picked two just for fun. One is about the anomaly detection, to be more precise, the fan malfunctions. So you have basically a sensor that kind of listening to the fans in the system, and if if the fan starts behaving wrongly or suspiciously, then you get a message. The problem actually has two parts. One part is that you need to detect, which means the DSP signal processing, and also kind of recognize the signal. And then the second part is actually detection itself, which has been done using the AI-oriented algorithm. So in the end of the day, we came up with the roughly 40 instructions. Part of it is the DSP-oriented instructions. Part of it is the AI-oriented instructions. And all in all, when we put this together, we get really nice speed up. It's more than 4x, as you can see. Energy consumption dropped down significantly, because suddenly you can do more in less power, in less time, and therefore the energy consumption is much smaller. You need to put new instructions in place, of course, so the area is bigger, because you added stuff. But all in all, if you look at the outcome, it's quite good, I believe. Another one that I like even more is just the exercise that we did for fun most of the time, and we kind of try to showcase the capabilities of the bounding customization. So I mentioned that we have a set of rules, but the rules are designed in a way that you can do a lot of things with it. And this kind of proves the point. So I'm pretty sure that you know NES, the gaming console. If you look inside, you will find out that there is a CPU in it, which is the 6502 processor, and there are a couple of different blocks as well, like pixel processing unit and audio processing unit. You can take all of it, you can find the emulator, and you can run the emulator directly on the RISC-V, and you can play the games. But what we did in this case study is that we took the processor, and we actually created the processor in the RISC-V. So we have a RISC-V processor that runs processor in it. All of it follows the rules that I mentioned a while ago. So we have the instructions, we have the internal registers, and then we have a communication channel between the main RISC-V and the model 6502. We did it during a single week, just kind of prove the point. We put that into the FPGA. We have virtual prototype. You can actually play that on the FPGA board. And if you look at the results, besides the fact that it was done in a week time frame, by a single engineer, you get a very decent speed up on the frame. The energy, of course, drops down as well because you're faster. And then, yes, you need to pay the area back because you have actually CPU within the CPU. So it has to be bigger. But it's kind of, again, the main point of this one is to showcase that you can do not just the simple instructions like DSP or this AI stuff, but you can also do the whole CPUs and still following the rules. And we still guarantee that you don't have to re-verify the rest of the CPU because that stays safe. Which leads to the last slide that I have today. So I'd like to kind of mention a few key points that preferably you will remember. So thanks to the fact that we have to deal with more and more demanding demands on the performance and the speed and these sort of things, we need to kind of look for the solution for it. And one of the solutions is heterogeneous compute, where RISC-V fits really, really well, thanks to the fact that you can customize it and can still reuse the binaries outside because we have profiles and all sorts of other things. So this is all good, really good. We believe in automation in Codasip, so the more you can automate, the better. And in this case, we have a tool by which you can, again, customize the CPU and get the RTL and get the SDK from the single description of the CPU. So you don't have to have necessarily several descriptions. And we came up with a boundary customization approach or methodology that builds on a set of rules that are captured in the configuration. So then if you would like to tune the rules, you can. We have several use cases that proving the point that actually this is really well. And our customers, they can do a bunch of different things with this, like in the motor control stuff, the AI stuff, pretty much all over the board. And which kind of gives really nice power, not only to the hardware guys, but more importantly to the software guys, because they can play with that as well. Because now it's much easier to add instructions and try to see what they will do for you in the end of the day. And with that, I'd like to thank you for your attention and ask for questions.